All right, we can now move on to section 4.3. This marker is not good. Let me get it a 4. Section 4.3, Maxima and Minima. So we're going to start talking about the graphs of some stuff using the derivative, which is very cool, and it's a very neat way I can use everything we have learned so far in this class. It's a very helpful way, as we are going to see. So we're going to start with a definition. Let C be an interior point in the domain of F. So what I mean by that is if, let's say, the domain was like 1 to 9, it just means it can't be 1 or 9, right? It's either something, so it is something between them, okay? So it cannot be 1 or 9. So something like 2, 3, 4, 1/2, that kind of thing. It just can't be 1 or 9. So we say that C is a critical point. So then we're going to be using these a lot, and they are a big deal. Critical point of F if the derivative at that point C is equal to 0, or the derivative at that point is undefined. That's going to be a critical point. Okay? So what I want to do now is I want to practice finding these things. So let's look at an example. Find the critical points of the function f of x equals 1/3 x cubed minus 5/2 x squared plus 4x. 1/3 x cubed minus 5/2 x squared plus 4x. So to find these points, it's where the derivative is equal to 0 or where it is undefined. Well, if I look at this, there is nowhere where oh, actually, first, sorry, we have to find the derivative first. My bad. Let's do that first because that's what they both want, right? So let's do this first. F prime of x. We're going to bring our power down to the front. 3 times 1/3 is a 1. So that's 1x. Now it's squared because it's 1 less, right? Same thing over here. Bring down our 2. 2 times 5/2 is just a 5. So that's going to be 5x plus 4. Okay, now looking at this, I can see here there's nowhere on here where this is going to be undefined, right? That might happen if I have like 1 over x, in which case we say x is undefined at 0. But that doesn't happen here, and so I'm fine. I don't have to really worry about that. Don't have to worry about this. So I just want to know where is it equal to 0. So to figure out, just set that equal to 0 and solve it for x. So I can see right here I need the factors of 4, whose sum is equal to -5. That's going to be -4 and -1. So x minus 4 times x minus 1. Set each of those equal to 0. Getting ahead of myself. And solve those. So for this one, I would add 4. We say x equals 4. Add 1, and we get x equals 1. Therefore, the critical points occur at x equals 1 and x is equal to 4. So again, all we did there is take the derivative and then set it equal to 0. That's all I've got to do to find what the critical points are. Let's do another example. Find the critical points of the function f of x equals x squared minus 1, that quantity raised to the third. So just like I said, first things first is I have to find the derivative of that. I can use the chain rule here because I have some stuff raised to the third. So I can use the power rule, bring the 3 out front. That makes it 3. Leave this stuff, and my power is now to the power of 2. But then by the chain rule, because I have some stuff in here, I have to multiply that by the derivative of that stuff. The derivative of x squared minus 1 is 2x. Which it might be helpful to write this. 3 times 2 is 6, so that's 6x times x squared minus 1 squared. So now all I've got to do is just set this equal to 0. Well, the good thing about this one is the factors are already there. So that's very helpful. So I can just set each factor equal to 0. Divide by 6 here. X is equal to 0. For this one, add 1 on both sides. X squared is equal to 1. Since it's x squared, just take the square root of it. So x is equal to plus or minus a 1. So for this one, the critical points occur at x equals -1, 0, and 1. Again, all that we did, take the derivative and set it equal to 0. Another example. Find the critical points of the function f of x equals 4x over 1 plus x squared. 4x over 1 plus x squared. So again, let's find the derivative of that. This is a quotient, and so I'm going to need the quotient rule. So remember, that's low d high, high d low. Low means we're going to keep the denominator. D high means the derivative of the top part. The derivative of 4x is just 4 minus high d low. So leave the numerator multiplied by the derivative of the denominator. The derivative of 1 plus x squared is 2x. All of that over the denominator squared. Let's try to simplify that sum. Let's distribute this 4. So 4 plus 4x squared minus 4x times 2x is 8x squared. So the simplified form of this is 4 minus 4x squared all over 1 plus x squared squared. So what I want to know is, where is this undefined? Since I have a fraction, now I have to actually worry about that. So where is it undefined? Well, that's where the denominator is equal to 0. So set the denominator equal to 0 and see when that happens. I have stuff squared, so let's take the square root. So 1 plus x squared is equal to 0. Subtract 1 on both sides. X squared is equal to -1. Take the square root, and x is equal to plus or minus. That would give me I. But remember, I'm looking for a point. I cannot plot a point of I, and so that didn't help me. So I get none from this. But now I have to also see when it is equal to 0. Remember, if a fraction is equal to 0 when the numerator is. So just set the numerator equal to 0. Subtract 4 on both sides. -4x squared equals -4. Divide by -4. X squared is equal to, that gives me 1. square root of both sides, x is equal to plus or minus 1. So the only critical points that I get are x equals -1 and x equals 1. So now that we know how to actually find what the critical points are, let's see how I might use them. Okay. To do that, we have some words I need to define, but the definitions are really long, so instead of trying to write them out, I have typed them. All right, this first one right here, let f be a function defined over an interval I, and let C be within I. That's what this means. It just means C is within that I. So if I was like, if I had I was equal to the interval, I'll just say 2 to 10, this means C is somewhere between those, is what that sign means. Okay, so C is something inside of this I. We say f has an absolute maximum on I at that point C if f of C is greater than or equal to f of x for all x inside of I. So basically, this means the maximum is the highest point. That's basically what this means. This is the highest point. But it is the absolute highest point. We say that f has an absolute minimum on I at C if f of, this should say C, if f of C is less than or equal to f of x for all x inside of I. So the minimum is the absolute smallest point, the lowest point. The minimum is the lowest point. Both of these are called absolute extremum. So basically what this means is, let's say I had a graph. This graph starts, let's say right here, and it does this number. It does all kinds of pretty neat stuff, and stops right here. Okay. The absolute maximum would be this highest point. That is the absolute maximum. And then the absolute minimum is the lowest point. That's what all of this means. We have another term that kind of relates to this. A function f has a local maximum at C if there exists some I with C such that I is contained in the domain of f, and f of C is greater than or equal to f of x for all x inside of this I. Function f has a local minimum at C if there exists an open I containing C such that I is contained in the domain, and f of C is less than or equal to f. Absolute max and the absolute min. A relative max and a relative min means those are the maxes and mins for a certain point, okay? So what I mean is it's not the absolute highest point for the whole thing, but in a tiny piece of it, it is the highest point. So what I mean is if we look right here, this goes up and then goes back down, right? So this is a peak. It's not the highest peak, but it is a peak if I look at just a small bit here, right? So this point would be a relative maximum because it is a peak. It's not the highest one, but it is still there. Same thing right here. This one is a peak, so this is also a relative maximum. Same thing over here. I would also call this one a relative max. It just happens to also be the absolute maximum. Same thing here. There's a little trough right here. So this is a relative minimum. Same thing here. Relative minimum. Same thing here. Relative minimum. But notice the absolute smallest point isn't any of those troughs, right? It happens to be this point where I stop because this is the absolute smallest point on that graph. Okay? But I can't call this a relative because it's not a trough. It doesn't like swoop up, right? So this is just the absolute minimum here. Okay? So let's see what I notice about each of these points here. So the absolutes are either at one of the endpoints, because I could see it could have been here, but it's not because I have this high point here. But it could have been here, or just like I see right here, the smallest point could be right here. So it's either the endpoints, or it's where I have a trough or a peak. Well, let's look at each of these points right here, what I see. If you look at this point, the tangent line right here is flat. The tangent line right here is flat. The tangent line right here is flat. The tangent line's flat, flat, and flat. Remember we said when the tangent line is flat, that means its slope is 0. So these happen when the derivative is equal to 0. So what this means is this really neat and helpful fact right here. Let f be a continuous function over a closed bounded interval I. The absolute max of f and the absolute min of f must occur at either the endpoints or the critical points. What this means is to find the absolute max and min. All I do, first evaluate f at the endpoints, because remember we said it could be there. Could be there, right? Number 2, find the critical points, because we said it might happen there. Critical points. And evaluate f at each of those. Once I do that, and smallest between all of that. Let's look at some examples of doing that. Determine the absolute max and min for each of the following. We're going to do a few of them. The first one we're doing, part A, is for the function f of x equals negative x squared plus 3x minus 2. And we're doing that over the domain 1 to 3. Okay, so the first thing is I've got to see what it is at the endpoints. So plug in a 1. F of 1 is equal to negative 1 squared plus 3 times 1 minus 2. 1 squared is 1, so negative 1 plus 3 times 1 is 3 minus 2. Negative 1 plus 3 is 2, minus 2 is 0. Now plug in a 3. Negative 3 squared plus 3 times 3 minus 2. 3 squared is 9, so negative 9. 3 times 3 is 9, so plus 9 minus 2. Negative 9 plus 9 minus 2 is negative 2. So I've done that. That is my first step. So now I've got to find what the critical points are. Remember to do that, take the derivative, f prime of x. Bring the 2 down, so negative 2x plus 3. and set that equal to 0. Solve it for x, subtract 3, negative 2x equals negative 3, divide by the negative 2, x equals 3 over 2. So now I've got to also see what it is at 3 over 2. So now do f of 3 over 2. That's negative 3 over 2 squared plus 3 times 3 over 2 minus 2. 3 over 2 squared is 9 over 4 because 3 squared is 9, 2 squared is 4. 3 times 3 over 2 is 9 over 2 minus 2. We need a common denominator of 4. To get 4, multiply this one by 2 and multiply this one by 4. So negative 9 over 4. 9 times 2 is 18, so plus 18 over 4 minus 8 over 4. Negative 9 plus 18 is 9. 9 minus 8 is 1, so 1/4. So when I'm looking for the absolute maximum, I'm looking for the highest number that I got over here. I got 0, I got negative 2, and I got 1 over 4. So the absolute max, the highest point there, is 1 over the 4. So the absolute max happens at x equals 3 over 2, because that's the highest one. So when I do the absolute minimum, I'm looking for the smallest one, right? So I'm going to look here, I got 0 here, I got negative 2 there, and I got 1 over 4 there. The lowest one of those is the negative 2, which happened at x equals to 3. And there we go. That's how I find the absolute max and the absolute min. Let's do another example. Help if I open my marker. Example. Oh wait, we already wrote it down. That last one was part A, this one's part B, doing the same thing. F of x here is equal to x squared minus 4x plus 3, and we're doing that over the interval 1 to 4. So again, the first thing, plug in a 1 and plug in a 4. F of 1 is equal to 1 squared minus 4 times 1 plus 3. 1 squared is 1, minus 4 times 1 is 4, plus 3. 1 minus 4 is negative 3, plus 3 is 0. Now plug in 4. F of 4, 4 squared minus 4 times 4 plus 3. 4 squared is 16, minus 4 times 4 is 16 plus 3. 16 minus 16 plus 3 is 3. And then now I have to find what the critical points are. Remember to do that, take f prime of x, which will give me 2x when I bring the 2 down, minus 4. Set that equal to 0. Solve it for x. 2x equals 4. Divide by 2 and you get x equals 2. So now I've got to check 2 and see what happens at 2. So f of 2 is equal to 2 squared minus 4 times 2 plus 3. 2 squared is 4. 4 times 2 is 8 plus 3. 4 minus 8 is negative 4 plus 3 is negative 1. So when I write down what the absolute maximum is, I look for the largest one. I got 0, I got 3, and I got negative 1. The largest one of those was 3. So it happens at x equals 4. Looking for the absolute minimum, I got 0, 3, and the negative 1. So the smallest one is this one at x equals 2. There we are. So it isn't too bad once we do a lot of these. It honestly doesn't take as much work as you might think it does. One more example. So this would be part C. Minus 3x to the 2/3 over the interval 0 to 2. 0 to 2. Okay, first thing, plug in 0. F of 0, 0 squared minus 3 times 0 to the 2/3, which is 0 minus 0. So that's what I get there. Now plug in the 2. F of 2 is equal to 2 squared minus 3 times 2 to the 2/3, 2 squared is 4, minus 2 to the 2/3 isn't anything that's like super clean and clear. So we can just leave that and plug it into a calculator to see what that is. So if you plugged it into a calculator, 4 minus 3 times 2 to the power of 2/3 is about negative 0.76. That'll help us just see if it's the smallest one or whatever. So now I have to find the critical points. So we take the derivative, bring the 2 down here, and we get 2x. We've got to bring down 2/3. 2/3 times 3 is just 2. X to the power of. If we decrease this by a 1, 2/3 minus 1 is negative 1/3. So to set that equal to 0, it might be helpful to write it as 2x minus 2 over x to the 1/3. And then we can set that equal to 0 and solve that. So, set that equal to 0, we can add 2 over x to the 1/3 on both sides. So 2x equals 2 over x to the 1/3. We can multiply that by x to the 1/3. So x to the 1/3 times x, that's 1/3 plus 1. So 2x to the 4/3 is equal to 2. Divide by 2, x to the 4/3 is equal to 1. So that must mean x is equal to 1. Remember, we must also find where it is undefined, right? So in this case, x to the 1/3 cannot be equal to 0, which would mean x cannot be equal to 0. But I don't actually have to worry about that one because I already plugged it in here. So I don't really need this one. It didn't help me out. So just plug in a 1. 1 squared minus 3 times 1 to the 2/3. 1 squared is 1. 1 to the 2/3 is 1 times 3 is 3. So negative 2. So when I look at this and I find the absolute maximum, the largest one that I found 0, negative 0.76, and negative 2. So the largest one would be 0. So that happens at x is equal to 0. And the absolute minimum, the smallest one of these, is the negative 2. So x equals 1. We are going to use this skill a lot whenever we draw graphs in section 4.7, I think it is. We're going to use this a lot. So let me know if any of that does not make sense.